Let's make a start for this more detailed session on research. My name is Byron Byrne. I'm a professor at Oxford University and I do research mostly in geotechnical engineering, mostly for offshore wind structures. So I'm very pleased to chair this session on research. We're going to start with some of our early career researchers. This is the next generation of people that will lead research into the future. We had a very vibrant day yesterday, the ECR forum. Lots of energy, lots of ideas, about 50 people. It was really very encouraging. What I would say is that in the room across the way over there are the posters. There is a poster competition and we invite you to mark the posters or at least select your top 3. There's some slips of paper that you can put your top 3 on and there is a voting box. So please do that and we'll hopefully select a winner for some prizes later in the day. But your input, very important. We want to be fair and select the best poster. So we're going to start with some quick-fire presentations from the early career researchers. This is really a taster of the work they are doing. It'll be about a minute per person. There's 5 of them. They'll briefly introduce themselves and talk about their research. So I'll ask them to come up in order. They'll have to line up. And we'll get through it pretty quickly. We will then have 4 longer presentations of about 8 minutes each. And then we'll have some questions at the end for the presenters. So please make sure you store up your questions. We'll have about 15 minutes for question time. So let's use it up. So I'm going to hand over to Abby.
Hello, my name is Abby Bateman. I am a postdoc at the University of Southampton, working on reliability-based design for offshore foundations. So even within a single soil unit, strengths can vary by up to a factor of 100 over distances of meters to kilometers, and even more between layers. So this variability can look something like the 3 examples here. So if we consider the simple case of a surface foundation on these 3 materials, do you want me to take it? Yeah. So if we consider the simple case of a surface foundation on these 3 materials, but we know nothing specific about the actual foundation site, applying the same design codes can result in 3 very different probabilities of failure, as shown on the left. So site L is particularly uncertain because you may be founding on a large area of weak or strong material, compared to site S, where the spatial variability averages out across the foundation size. So instead, site-specific testing for each foundation can provide a specific snapshot of information for each site based on the local ground conditions. And this shows you can have much improved reliability for a site like site L, but actually slightly reduces the reliability for site S because of bias. Thank you.
Hello everyone, my name is Yang. I'm a research fellow at the University of Plymouth, working on EcoFloat Frontline project. Frontline is basically focuses on ecological impacts of floating offshore wind in the Celtic Sea. So in the Celtic Sea, the offshore floating wind are planned largely overlapped with tidal mixing fronts, which act as hotspots for nutrients, zooplanktons, fish, up to seabirds and marine mammals. So the large scale of the wind farm infrastructure into the water can alter or change the nutrient structures or water columns, and therefore generating cascading effects on fish and all of these animals and the seabirds. So we have 3 work packages in the project. Basically, we use autonomous vehicles with different sensors, and we also use satellite remote sensing technology. For fronts, we also use digital air surveys for seabirds and marine mammals, and we also assess the fishing activities and their social impact in the project. Thank you.
Hi, my name is Nishme and I'm a postdoc at the University of Oxford working on the Supergen tidal turbine benchmarking project with Richard Wilden. Today my poster is about the stage 2 unsteady loading in waves, where we've tested a large-scale 1.6 meter diameter tidal turbine in a variety of wave conditions. We've collected instantaneous torque, thrust, in and out of plane group bending moment measurements, as well as bending moments at 6 radial locations along the blade. And we've got some really exciting results, particularly a linear relationship between load fluctuation amplitude and current number averaged over the rotor plane, as well as a approximately linear relationship between the peak load phase lead and the frequency ratio between the wave encounter frequency and the turbine rotational frequency, which we believe represents added mass effects, as shown in the difference in the elliptical relationship there. So if you want to speak any more about the benchmarking project, please come and ask me questions about my poster. Thank you so much.
Hello everyone, my name is Burhan Yıldız. I'm a postdoc at the University of Liverpool. In this project, we aim to deploy wave energy converters at sheltered environments with the aim of low cost and operation and maintenance. Here you can see the settings. We use the cylindrical board to represent the wave energy converter. It's a point observer type, and it is very close to the wall. So that in this kind of settings, the viscosity effects will be important. We conducted a numerical model, and in this numerical model study, we aim to have convergence in terms of turbulence quantities. So that we had a high fidelity model, and we, as you can see from this figure, we obtained a convergence in our mesh in terms of turbulence kinetic energy. And by using this converged model, we applied our cases at different wall distances at different wave settings. And in some configurations, optimal wide positioning can increase captured power by up to 10-fold. Thank you.
Hello everyone, my name is Elias Arkandoulis from the University of Southampton and the Institute of Sound and Vibration Research. Why would someone from Sound and Vibration Research be venturing into offshore renewable energy? I'm trying to build an interdisciplinary bridge from what I've learned in aerospace engineering regarding passive flow control techniques that have been highly effective at mitigating vortex shedding and turbulence production. Is the key flow physics of aerospace environments relevant and transferable to offshore renewable energy? I present 3 projects that I've been working on. On the upper right is a structured porous breakwater conducted at the Coast Lab at the University of Plymouth, where I was able to quantify the ability of a porous structure to attenuate wave loading and its reflection and transmission coefficients. On the bottom left, for a buoyancy column of a floating wind turbine, a structured porous material that significantly suppresses the unsteady loading of waves for a series of wave-train wave numbers. And finally, and my most recent work has been funded by the Supergen ECR funds, scale mitigation using a patent-pending porous material that generates a significant reduction of scour from a fully developed scour jet, displaces the vortical energy, offsets the scour, thereby protecting the original structure. If you have any questions regarding the latter projects I presented here, please come see me in my personal lab today. Thank you very much.
Thank you very much, and well done for sticking to the 1 minute, which is a very tough ask, but importantly, very well done. So we are now going to move on to some research presentations. These are slightly longer presentations, a bit more in depth. Of course, if you want to speak to any of these people about their research, go and see them at their posters, and you can get into a lot more detail of that research. So we're going to start with Benjamin Williamson, who is from the University of Highlands and Islands. He's an associate professor, and he will be presenting on monitoring systems for floating tidal turbines. Over to you, Benjamin.
Okay, well, thank you very much for the introduction, Byron. It's really great to see you all. I'd like to gratefully acknowledge funding from the Supergen Hub Flexible Fund and all of my co-authors. I know many of you from research on offshore wind. What I'll be talking about here is environmental monitoring for floating tidal. So the risk of animals colliding with tidal stream turbine rotors is still a significant barrier to consenting at most sites globally. For seabed turbines, we often use upward-facing imaging sonar for tidal detection. There's a picture at the lower left of the slide of some of our work around hydro, the Atlantis turbines using seabed platforms. And we try and supplement this with optical cameras for target identification. But floating tidal turbines, of course, allow access to deeper water sites, easier installation, O&M, and potentially also greater efficiency from accessing faster near-surface flow. But they present quite a few environmental monitoring challenges compared to seabed turbines. These faster flow speeds and entrained air, so bubbles near the surface, naturally present in high-energy tidal stream sites, and a lot worse around turbines, all compromise our conventional monitoring techniques. The fact that the whole platform's dynamic as well and moving around makes it much harder to monitor from a static seabed upward-facing platform. We've got limited existing data and limited transferability of techniques and results, but floating tidal gives us some amazing opportunities. Sensor access, of course, is much easier, so we can really accelerate progress for the whole industry. And powering communications connectivity is much more straightforward. So in the project, we set out to validate robust environmental monitoring techniques. And we focused on imaging sonar. What we're trying to do here is optimize the system to detect animal interactions in the rotor-swept area. And ultimately, what we're trying to do is support scale-up and build-out of this industry, working in particular with orbital marine power initially, as they develop their sites at EMAC, at Westray, and into the Bay of Fundy, and now building on this with Natural Resources Canada funding to develop a regulatory toolkit for the Bay of Fundy developments. So our methodology, we pole-mounted an imaging sonar and a camera over the side of the O2 turbine operational at the full awareness at EMAC in Orkney. You can see the pole mount here on the right-hand side of the O2 turbine. There's a picture on the water. Now on the left-hand side, this is a downward-facing imaging sonar and a camera alongside. And if we look at this top image here, where we're looking sideways into the flow, then the green arrow here, this is our downward-facing sonar. So on the flood tide direction, we're taking measurements of animals upstream of the rotors, potentially an approach to the rotor-swept area. On the outside, the sonar's downstream. And so if we wanted upstream coverage for flood and air on the O2, we just mount another sonar up here, where the ACP is. But actually, because the O2X turbines, the future turbines, will yaw with the tide, we'll always be taking measurements upstream as the rotors if we mount here. We can look at the bottom of the screen and look into the flow, or the flow coming out of the screen into the rotors, and you can see the green lines here show the coverage, the imaging sonar, and on the left-hand side here, this is the normal rotor-swept area with the sonar swept. So for the methodology, we deployed this for 4 months last year, thanks to some incredible help from Orbital and EMAG. And what we set out to do was quantify the signal to noise, so basically the detectability of targets. And if we can understand how detectable targets and animals are across tidal state, met-ocean conditions, turbine operation, then we can inform transferability. We can predict how well this will work in some of these other sites that I talked about. So the data processing goes through a few different steps that I'll very, very quickly run through. So first of all, we need to deal with that entrained air. This varies as a function of tidal and met-ocean conditions. So as flow speed picks up, these bubbles entrained at the surface get worse, they get deeper in the water column. When we've got wind against tide, tide against wave, things get a lot worse as well. Although the sonar swath, which is this red triangle here, nominally doesn't include the rotors, we have what's called beam side load. We do get returns from the rotors, the turbine legs, and wake effects, and then of course the turbine cable and mooring, before finally then we can deal with our automated target detection. These give you some examples of what the data sets look like. These are 30-minute maximum images, so very much a worst case that we try and visualize some of these artifacts. So on the left-hand side, here's an example return from the rotors, thanks to the side lobes of the sonar. It's an artifact of how it works. In the middle, as the sonar moves the slack water, you can see the mooring lines and power cable drifting into view. And then on the right-hand side, hopefully you can see it in the slide, we've got all of these returns near the surface. These bubbles, this entrained air that start to dominate the image, and we really need to mask these out. So what we've done so far is been able to delineate entrained air, so we can mask this from our processing for trying to detect animals. So up here at the surface, this is a single ping, about 2.5 meters per second flow speed. Here's the bubbles at the surface, and what we're looking for here is this threshold in intensity. How can we mask out the bubbles and then look to the clearer water column lower down, looking for animals down here. Critically, we developed this as a paint-by-paint mask. So as these clouds of bubbles come through, we can look in between the clouds of bubbles for animals. We can look spatially deeper in the water column, rather than just cropping out whole periods of monitoring above the cutting speed. We developed target tracking algorithms. So very briefly, on the left-hand side, an initial detection step. And this is looking for candidate returns that might be animals. What we're trying to do here is prioritize what's called recall. So from a regulatory perspective, we really don't want to have false negatives. We want to be missing animals that might be coming through. We then go through a tracking step in the middle, and then on the right-hand side, a user-controlled and adaptive filtering step, where we're trying to then improve the precision. And so precision is trying to cut down on false positives, trying to reduce the burden for a reviewer or a regulator to look through these massive data sets. And here's a quick example of what it looks like. So on the left-hand side, this is our initial detection step. So the sonar's up here, the flow is going into the screen as we look at it at the moment. Again, it's about 2.5 meters per second above cutting speed. We've got lots of candidate returns here, these red squares from a single ping. Lots of these spurious noise, reflections, artifacts, returns from the rotor, the legs. So we go through all of these filtering and tracking steps that I showed you before. We get to the right-hand side, where we've got much higher confidence that these are animals passing through the sonar swath after our tracking. What we can also do is categorize and prioritize, perhaps particularly from a regulatory perspective, prioritizing tracks where some part of it passes through the rotor swept area, plus a user-defined buffer. And then we can also threshold our targets into larger animals compared to very, very small returns. And so really as a bit of a proof of concept, this is a video at 2.5 meters per second. You can see the target coming through here. We've got much smaller returns in the centre here. But what you'll start to see is, yes, there's lots of noise, but we start to get these repeat returns, which are animals passing through the sonar swath, in this case with the flowing towards the rotors, and yet dealing with the entrained air and with all of the higher range returns. So where we've got to so far, we've been able to delineate and mask the entrained air. I think we've got robust target detection across the rotor swept area. The algorithms give us greater sensitivity than manual annotation from a human looking through this, particularly with a fainter or less distinct targets and tracks. But of course, classification, what these animals are from sonar data alone, is really, really challenging. So next steps are to characterize the camera performance, to optimize sensor position. Have we got them in the best place for our objectives? And we're planning some further trials to evaluate other imaging sonar models. And then ultimately, trying to pick up this idea of transferability to other sites, other turbines, and building on our collaborations with the Bear Fundy for Acadia University to gain that kind of funding. So I have to go very quickly, but I hope it gives you a few insights into what we've been working on. Thank you very much again to my co-authors, my funders, and I'd be happy to take questions later on. Thanks very much.
As I say, we will take questions at the end, so please remember them and store them up. So I think the next speaker will be Dr. Danny Coles, who's from the University of Oxford. He's a senior research associate, and he will be talking about tidal stream energy.
Okay, good morning everyone, and thanks Byron, and thanks to Supergen for the opportunity to speak today. This morning's session we heard a lot about the need for resilience in the energy system and diversification of renewable energy in order to deliver that resilience. And that's really what I'll be talking about today in the context of energy system modelling and the role that tidal energy can play in delivering that resilience and security. So I'd like to just start with what's motivating this work, and really I'm just pulling out here 3 key uncertainties that the National Energy System Operator have identified when it comes to planning the future energy system in the UK. The first one is hydrogen to power. So there's unclear evidence as to how hydrogen will achieve the necessary level of scale that's needed given the costs associated with hydrogen to power. And that's a really important aspect in this area of future system design, for the reason that hydrogen to power is one of the technologies that's looking to replace fossil fuels, dispatchable fossil fuels, to overcome some of the challenges around the variability in renewable supply. The second area NESO have identified is carbon capture and storage, and similarly there are still significant cost and technical challenges around CCS and how that will look in the future. And then finally, interconnectors, for the reason that the investment is uncertain and also the dispatch of electricity across borders is dependent on international planning. Today, I'm really going to focus mainly on the hydrogen to power aspect, along with other aspects of the energy system, but this is certainly, these other two areas are areas for future work that we're looking to work on. Okay, so when it comes to tidal energy, as I'm sure everyone is very well aware, it has these different characteristics to things like wind and solar, in the sense that it's cyclic, so we tend to see in the UK 4 very distinct periods of generation every single day. It's reliable in the sense that it's independent of weather, and then finally it's predictable from short to long timescales. So really the question here is, given that tidal has these characteristics, what system value do those characteristics have, and how does that system value weigh up against the cost premium of tidal? Because tidal is likely to always be more expensive from an LCOE point of view compared to solar and wind, for example. But if it's able to deliver these different system impacts, then maybe that makes it a viable option. So this work really builds on the good progress that's been made both within Supergen and projects like the Tiger project that have undertaken similar energy system modelling, and we're just taking it a little bit further in the ways I'll describe now. So we've been running UK scale energy system modelling using the Python for Power System Analysis software. Really the novelty that we're trying to deliver here with this work, there are 2 key points to that. First of all, we've taken the National Energy System Operator's future energy scenarios, so the latest scenarios that they've developed, so that's the holistic transition, electric engagement and hydrogen evolution scenarios. And these are 3 different scenarios that get to net zero using different mixes of technology, in summary. In general, there tends to be around about 75% renewable generation, and then the rest is made up using nuclear and bioenergy, and some CCS with gas, for example. The second area of novelty that we're implementing is implementing capacity expansion modelling within these energy system models. So what that means is, instead of adding a kind of arbitrary amount of tidal energy, for example, to the system and taking away an equivalent amount of wind, for example, and looking how the system performs, we're running the models to optimise the amount of tidal energy that's installed on the system, and also the amount of offshore wind that's installed on the system for a given capital cost for tidal energy. So what I'll do now is I'll just present some of the kind of key findings from this work based on running these 3 different scenarios with capacity expansion modelling. So first of all, just in terms of the mechanics of what's happening here with the model, we're running the model at different levels of capital cost for tidal energy. So that's shown on the x-axis here, running from high to low. And what's happening is, as the tidal capex is reducing, the model is deciding at some point, some threshold, to install tidal energy on the system, because the system value that it delivers outweighs its cost premium relative to offshore wind. And then at the same time, shown by the bottom plot, the amount of offshore wind installed on the system is actually reducing in order to minimise system costs. So that supply is balanced with demand, but using a more diverse mix of renewables. Okay. Now, obviously, the threshold as to where tidal energy starts to be expanded within the system depends on the future energy scenario that's modelled, and there's lots of complexity around that. But what we're seeing is very similar trends in terms of what's happening. Just going back to one of the key risks that NESO have identified, which is hydrogen to power. We've looked at how installing tidal on the system affects the amount of reliance on hydrogen in order to deliver power. And again, we're seeing that by introducing tidal into the system as a replacement for some offshore wind, diversifying that mix of renewables, the reliance on hydrogen dispatch is reduced significantly. So that has a significant impact not only on the system cost, but also the security to the system as well. Other knock-on effects from installing tidal stream are related to the performance of battery storage on the system. So the illustration on the top left here is just indicating the fact that in a period of one day, we get these very distinct four periods of power generation, with only around about a 1 hour slack window where power isn't generated. That makes tidal energy highly compatible with short duration storage, such as lithium-ion batteries, which tend to be the cheapest form of storage on the system. What this means is that the load factor of the batteries on the system increases, again, quite significantly as a result of introducing tidal to the system, and that's what's shown on the right-hand side here. And so this is an area that we're very much interested in and working further in, is understanding that compatibility between different technologies, those synergies that might result in benefits. Ultimately, what most people are interested in when it comes to system design is the system cost. So that's again related to this balance between cost premium and system value. And as you can see, what we're seeing is that as tidal capex reduces, the system cost is able to reduce as a result of those system impacts. What I'd like to do now, though, is link these tidal capex values to real-world data. So just finally, what's maybe most important to draw out of this presentation as a takeaway is that based on 2016 costs for Maygen Phase 1A that are published, the cost for Maygen Phase 1A was around about £900,000 per megawatt when taking capital cost as an annualised figure. What that means is that for tidal to be introduced into the system, to deliver that system benefit, the cost of tidal needs to reduce by around about 70% relative to that 2016 value. The Offshore Renewable Energy Catapult have done some work looking at cost reduction and how that reduces with cumulative deployment, and they estimate that by around about 750 megawatts, that cost will be reduced by around about 70%. And there's around about 400 megawatts planned in the UK and France in the next kind of 8 years or so. So that kind of gives some context to those figures. And then, yeah, okay, I'll maybe end it there. Yeah, okay, thank you.
Okay, thanks. Thanks for that, Danny. So our next speaker will be Dr. Catherine Kwa, who is a Royal Academy of Engineering Research Fellow based at the University of Southampton. Over to you, Catherine.
Hello. Thanks, Byron, for the introduction. Hi, everyone. It's nice to be here. So my research background is actually in offshore geotechnics, looking at seabed response over time, and then making anchoring systems more efficient for floating offshore renewable energy. But I took a little bit of time out from that research to pursue a science policy secondment with the UK Department for Energy Security and Net Zero, and we worked on enhancing science policy making on scaling up UK floating offshore wind. So just a little bit about the journey. I was inspired to do a science policy secondment after attending a Royal Society policy primer, where I learned a bit more about science policy making, but also got to meet other people who had been seconded into the UK governments. Met some civil servants there as well, who then put me in contact with the head of the energy engineering team. After that event, I had a call online with them and then was offered a designated secondment, which was really exciting. But the problem was that they couldn't fund my time, salary. So then I applied for some EPSRC Impact Acceleration Award account funding, was successful with that. Did a bit of training as well as part of the Supergen Masterclass on economic and policy analysis for offshore renewables with Donald Noble as well as Henry Jeffries, which was great. And then went off and did the secondment. It was 9 months, 2 days a week, part-time. And one of the sort of bonuses was having the energy engineering team come visit us at the University of Southampton just to see our facilities and have a chat. You can read a bit more about the experience in that link there, but back to the secondment, which looked at upscaling floating offshore wind. So what you can see on the screen here is a reference 22 megawatt floating offshore wind turbine that's been proposed by the US NREL. It's one of the largest in the world. At operating at capacity, it can power something like 10 to 20,000 homes. And you can see the steel support structure is really a very significant portion of that floating offshore wind turbine. It has a mass of 24,500 tons, a material steel construction cost as of December 2025 of about £15.7 million. And there's sort of three main components: the tower, the floater, the chain mooring lines, and you can see the breakdown of the size and mass of those components there. But at the same time, the UK, as you know, has really high potential for floating offshore wind, and we need floating offshore wind to unlock that 34 gigawatt target by 2040 as set by the government, because it gives us access to deep waters further from shore, also the ability to generate wind power both on the east and west coast of the UK. But one of the challenges is that it's not currently commercially viable to do farm-scale floating offshore wind. You can see from the levelized cost of energy, floating is more than double that of fixed bottom, and a significant portion of that cost is because of the material cost in the support structure, which you can see is about 10 times that of fixed bottom. So the aim of the secondment was to perform a feasibility study to explore the sorts of reductions we could get in the relative capital cost for floating offshore wind by using AI-like methods. And pretty much what we found is that it could be possible to reduce the capital cost of floating offshore wind by 18% and its total mass caps by something like 10%. And here's a bit of an outline of the methodology we used. So we modelled, first of all, a reference 22 megawatt floating offshore wind turbine in ASHES, which is an aero-servo hydroelastic simulator, and then took a bit of a holistic approach to try and vary the support structure design. So try and simultaneously change thickness, so wall thickness of the tower and floater components, thickness of the chain, as well as look at the different materials that we could use in the floater and the tower components. And then automate the optimization design procedure by using a single objective genetic algorithm. Inbuilt into that was an unfactored ultimate limit state analysis, with the main goal of minimizing the material steel or material concrete or welding costs. And here on the screen you can see a bit of a visualization of the single objective genetic algorithm. So imagine each of those red dots is a floating offshore wind turbine design. The collection of red dots is a population of floating offshore wind turbine designs. And they all have a range of material cost, welding and costs associated with them, which is quite well spread within the design space with maximum and minimums. And what the genetic algorithm is trying to do is define the minimum cost and then collect all the solutions towards that minimum cost and converge towards that with each passing generation. And what was really nice is that we could look at the genetic algorithm searching for the optimized floating offshore wind turbine solution. So on the x-axis we have a reduction in floater thickness relative to the reference 22 megawatt floating offshore wind turbine. On the y-axis on the top row, that's reduction in tower thickness. The bottom row, y-axis, reduction in chain thickness. And then the colours that you can see of the dots in the top row are the tower material, bottom row is floater material. And pretty much what you can see is that there's a range of floating offshore wind turbine design support structures that are being trialled initially, but with each progressive generation, the more expensive solutions are dying out until we eventually converge to that solution at the end of the 7th generation. And what that looks like is summarised here. So here's a breakdown of the optimised floating offshore wind support structure design by its components. So steel tower, composite high-strength steel, and concrete floater, steel chain with thickness reductions there relative to a 22 megawatt reference floating offshore wind turbine. And that's pretty much how we got to our conclusion that we could possibly reduce the capital cost of the support structure by 18% and its mass by 10%. You can read a bit more about the detailed work and technical work in our conference paper that I'll also present at the OMA conference in Tokyo in June soon. And of course there's future work. We would like to try different floater configurations because there's a lot out there. Try other materials and objectives, like actually focus on minimizing mass or minimizing the carbon emissions that are involved in the support structure design. Include fatigue in the floating offshore wind optimization procedure. And more generally, DESNZ was interested in using these sorts of optimization algorithms for other decarbonisation challenges. And this project was a case study specifically for floating offshore wind. And now some implications for policy. So I think the bottom line is we need to unlock 34 gigawatts of offshore wind by 2040. The UK has a really high potential for floating offshore wind. Now we need commercial scale floating offshore wind to actually achieve this. And the challenge is that it's currently a bit too expensive, but maybe it doesn't have to be as expensive as we think. So just back of the envelope sorts of calculations. Let's say that 34 gigawatts is achieved by these 22 megawatt floating offshore wind turbines that have been optimised. So we need 1,545 floating offshore wind turbines. Each one perhaps could have a 2.8 million cost saving per optimised floating offshore wind turbine. So that could come up to a potential cost saving of 4.3 billion in optimising the floating offshore wind turbine support structure design. So this is work that's worth doing. And then sort of more generally to encourage DESNZ to keep supporting cross-sector and cross-disciplinary floating offshore wind research, design and manufacturing, which they really do. We're all here at Supergen as an example. Also there's the catapults, there's plenty of other UK-based sort of consortiums that bring together academia and industry to innovate and solve problems in the offshore renewable energy space. So thanks for listening. You can ask any questions about the secondment experience as well. Yeah, please just reach out. Thank you.
Thank you very much, Catherine. So our final speaker for this session will be Professor Will Coombs, who's from the University of Durham, and he's going to be speaking about burial cable as soon as he changes a computer over.
Apologies for the...
There's always one.
Yeah. Thank you, Byron. Okay, thank you for the introduction. And apologies, I had to switch the computers. We had issues with my file transferring. So today, I just want to give you a bit of an overview and some key results from a research project I've been leading over the last 3 years in collaboration with researchers at the University of Dundee and the British Geological Survey on offshore cable burial, how deep is deep enough. If we start off with an image of the waters around the UK, and what you can see in these white lines are actually white dots, is basically the shipping traffic. And if we overlay in one area of the southern North Sea, the current telecommunication, power cables and some future offshore wind sites, you start to see there's a pretty congested seabed and also just seas in general. And this is only going to increase in terms of congestion as more wind farms are deployed, more interconnects are constructed, and also there's more connectivity within our own network using offshore cables. However, there is the potential for accidental interaction between shipping traffic, particularly shipping anchors and some of these cables. As I say, some of this is often accidental. This is a historic case now where a ship in storm conditions dragged its anchor and damaged the interconnect between UK and France, but also deliberate sabotage is a growing concern with deliberately dragging shipping anchors in order to damage subsea cables. The primary way that subsea cables are protected, offshore, is by burying them below the seabed. And the depth of burial is really a compromise between making sure that you're managing the risk to that asset versus the cost of installing to a greater depth. If you go deeper, you need larger machinery, larger vessels, more complex operations, and it drives up the cost. So the way that burial depths are reassessed, and this is in the UK, but in many other countries around the world, is to use the Carbon Trust Cable Burial Risk Assessment methodology. And within that, anchors are identified as the primary threat to subsea cables. Anchor penetration is estimated by this quite simple equation where this L is the fluke length, that's the pointy bit on the anchor which penetrates into the seabed. We have the opening angle, and then we have this seabed factor SF. And the guidance suggests a value of 1 for sands and a value of 3 for clays. And geotechnical engineers in the room may be a bit surprised by how simplistic this is. But the guidance is pretty open in that it says that this is an area for research. These seabed factors are potentially not conservative or actually over-conservative in some areas, and more research needs to be done. And that's really what motivated this particular research project. So the way that we tackled this was through a combination of physical testing in a geotechnical centrifuge at the University of Dundee, and we used an unlimited set of test cases to then validate new numerical modelling techniques developed at Durham University, where we can then do much more comprehensive parametric sweeps of different soil conditions. So I'm going to talk primarily about the numerical modelling because that's what I do. The technique we use to do the numerical modelling is a method called the material point method. For the engineers in the room, it's very similar to the finite element method, but it's much more suited to modelling very large deformation soil structure interaction problems. Really, this is an area where there's no commercial software out there at the moment that can really reliably solve these problems. So how do we start? Well, in order to sort of generate a digital seabed for our numerical simulations, we need to somehow populate that with properties. And what we do there is we use the same site investigation techniques that we use along a cabling route to make sure that the digital seabed we're creating matches the experimentally observed behaviour of the seabed. What you do in a cone penetration test is you push a conical tipped probe into the seabed and you measure the penetration resistance as you increase in depth. And so we use experimental results, again conducted in the same centrifuge where we did the anchor test, to then calibrate our numerical model, and here you can see the responses from very loose to very dense sand seabeds. Once we have that calibrated sea state, we then do our anchor simulations, and here you'll see two videos of two different anchors, a Hall anchor and an AC-14 anchor. These anchors have been selected because they're the most common shipping anchors used on vessels. And so what happens is as these anchors are dragged, they then start to penetrate into the seabed and at some point then reach equilibrium and steady state. And it's this ultimate depth that we basically want to know for different seabed conditions. These two anchors are tested in the same seabed condition, but you can see that visually they have quite different ultimate penetration depths. So looking at that in a little bit more detail, here we have a normalized plot of how deep these anchors are penetrating versus how far they've been dragged. It's normalized by the fluke length, and that's because the carbon truss guidance says really that anchor penetration is directly linked to fluke length. And we have four different seabed states, from very loose sand to very dense sand. And in comparison, the continuous line of the numerical results, the dots and the dashed lines are showing the final penetration depths that were achieved in the physical testing at the University of Dundee. So we get very good agreement, kind of validating our model in this loose and very loose sands, and maybe we slightly overestimate the penetration in these denser sands, and that's for the Hall anchor. And if we compare that to the AC-14 anchor, this is the one we can see has much greater penetration depths, particularly in loose sands and very loose sands, but actually pretty similar in dense sands. And if we contrast this to the current guidance, that's shown by that red dashed line. That's what would suggest how deep an anchor would penetrate in a sand seabed. And you can see that it's pretty good for very dense, it's actually very good for dense, but as soon as you move into these loose sands, then it starts to become non-conservative. And if we just overlay the results briefly, what you can see is if you move between a Hall anchor and this AC-14 anchor in loose and very loose sand, you see a 30% increase in the penetration depth, but the guidance would suggest these anchors would basically have the same amount of penetration. So it's much more complicated than just saying it's dependent on the fluke length of the anchor you're dealing with. So sort of overall observations, I won't read out the words here. Basically, my overall observations from this ongoing research is that just having a single factor to describe sand and clay is far too simplistic, and we need much more nuanced guidance on how deep different anchors will penetrate into the seabed based on the actual site-specific conditions along the cabling route. Really, the carbon truss guidance was developed now 11 years ago, and I think it's time that we kind of look at developing a new guidance document of how deep we bury offshore cables to make sure that we understand the risks of the currently installed cables, but also to make sure that the cables that we're putting in the ground now and in the coming years are installed to appropriate depth where we actually understand the true risk to those cables, particularly as we're moving into a much more uncertain time where there's both accidental interaction and deliberate sabotage. Acknowledgement of funding at the bottom, and also lots of people have worked on this research over the years. So I'll just close with this slide. There's a QR code here. If you want to understand more about this particular research project, you can scan that QR code. The image itself is of a high-performance mooring anchor because we're applying the same techniques to study their behaviour in different ground conditions. Okay. Thank you. Why don't you sit down?
Well, we're not just at the lunch break. We've still got about 10 or 15 minutes to sit down. No, leave it there. Leave it there. So we now have some time for questions. So I hope people have been storing them up and thinking about them. Who wants to start? Anyone? There's one over there.
I'll give way though because I asked one in the last session.
No, you're the only one with the hand up, so you have to go. Oh, okay, up here. Yep.
Really good talks, thank you. My name's Ian Masters from Swansea. Question for Catherine. You were optimising a single design, but there are lots and lots and lots of designs in the industry, some of which are much better than the one you started with. So how do you deal with that sort of step change, sort of structured innovation to different designs compared with that sort of single design optimisation? How do you do that trade-off?
Yeah, that's a good question, and you're very right, it is a step change. So I guess maybe I'll go back. The reason why we chose that particular design is because we found it in the time that we had quite easy to model in Ashes, because it has an open source sort of geometry, if you like, which then can go into Ashes quite easily. And it really is just another order of magnitude probably worth of simulations that would be required to then find, given all these different flow types, what would be a good flow type to then do. But I think what Desnes liked out of the secondment process was the framework that was built from just consider a particular case study of floating offshore wind turbine design. There is value in treating the tower, the flow string, the chains holistically in the optimization process, and a single genetic algorithm is a possible way of automating that sort of process. So they, I suppose, have that framework. It's coded in Python with some Ashes in there as well. And that's, I think, what they will try and take forwards to then choose also all sorts of other things that they were also interested in optimizing. Like one of the big ones was, well, if we have a high-strength steel and concrete floater, then concrete is cheaper and lighter, but then it also has a higher carbon footprint. So there were many other things that they wanted to also look at too. If that answers your question.
Okay, let's have one from over here. Richard? I think use your voice, Richard.
I'll be honest, I just got to shut it now. So, Richard Wilson, University of Oxford, did some fantastic research across the board, both in the posters and the presentations, and it really highlights actually the importance of the work we do in the research community. But actually, it's translating that research is the next key step. So could I ask each of the speakers to comment on actually the next translational steps and how you actually get what you're doing out there into the real community?
Yeah, sure. I can speak about the cables research. So we, throughout the whole research project, our project was really driven initially by Ørsted many years ago and their concern in this particular area. So we've worked throughout the project with a number of developers and consultants looking at how we transition the findings of the research into guidance for the industry. We're currently looking at developing an Innovate UK bid in order to try and develop a new approach to specify the variable depth of cables. We've also been supported by various EPSRC impact acceleration funding as well. So I think there are lots of mechanisms to do this, provided you go out and look for those things. And the most successful research projects that I've led have been driven by an industry question from the start. It's not something where I'm taking the noodling I like to do as an academic and then find a suitable problem. It's always been the other way around. That's my take on that.
Yeah, good point. And I think that's one of the reasons why I was inspired to do the science policy secondment, to understand other people's perspectives outside of academia on where this is going. One thing that was interesting though was learning about the translation in the sense of often what they were interested in is to, anyway during my experience, was the sorts of levers that they need to pull to then incentivize things that are worth doing to happen. And I think it was interesting going into the secondment because it was a very different job to my day job. And Supergen is great because it helps to translate all the chemical science into something which is then translatable, and there's many people in that translation process that then can translate it into something which policymakers then understand is something that's worth doing.
Hi Richard. So with the Mosaic project that I presented today, we've been making quite a strong effort to engage with policy. So actually on Monday we presented these results to the all-party parliamentary group meeting on marine energy. And then within the fellowship that I'm conducting, there are planned secondments both at DESNES and NISO. And the real purpose behind that is to conduct cross-model comparisons between the models I presented today and DESNES and NISO's own internal models in order to build confidence within these key stakeholders that tidal and wave energy can play a role potentially, and that there's reason for these key stakeholders to investigate that internally as well. And I think that would be a kind of success, if you like, for the project. So, yeah.
It's a really good point. I think for the floating tidal work, we're quite fortunate. It's really driven by industry, it's driven by the regulators. So because consenting these arrays adds the time, the cost, the risk of securing investment. We're quite fortunate in Scotland. We have adaptive management, survey, deploy, monitor. We've got these test sites like EMAC, so we can install the sensors on the floating turbine in Orkney, but then be driven by industry, the regulators, for example, in Canada, for what's required. So in Canada, they looked at some of the research that we were doing, they overhauled their consenting process through a task force, and then invested prior to these floating developers coming to the Bay of Fundy in trying to develop this regulatory monitoring toolkit. So I think translation is really important. I think for tidal, we're in quite a strong position in terms of Scotland and building on lots of previously funded research to now share these findings with other sites. So yeah, thanks, Richard.
Very good, thank you. And we'll go over here.
Yeah, thank you very much. My name is Steve Joey, I'm from the Celtic Sea Cluster. I wanted the two policy discussions, both the Catherine's and the Mosaic work. We've talked about cost reduction, and Guy from Great British Energy mentioned about cost of capital. I think cost of capital reduction is responsible for about a third of the reduction in offshore wind, so it's a big factor. The other thing that hasn't been talked about, I think you talked today, is that the supply chain for offshore renewables is critically dependent on hydrocarbons. There's not a single element of the supply chain that is not dependent on it. It's installation, operation, maintenance, materials, almost everything. Does your modelling in the case take account of that? Because I suspect that it would be a really important input, given that, for example, bunker fuel has gone up a factor of 2 and possibly 3. And I think it would be interesting to see if it made any difference to the conclusions.
Okay, Danny and then Catherine.
Yeah, thanks for the question. So the cost inputs within the energy system modelling are all based on DESNES's 2050 projections. So it's very much a kind of, what I presented today is very much a kind of base case, if you like, and I agree that that's going to be a really important sensitivity that in the future we need to kind of look at stress testing, if you like, as to if the cost of fossil fuels goes up, what does that do to the optimal solution within the model? So yes, it's on the agenda, but not something that we've looked at currently.
Yeah, I think you raised a really good point, and the modelling that I did not consider those factors that you mentioned, and it was raised as feedback when I presented the work as future work, I guess. But there is an awareness of that, I suppose, in the sense that it was given as feedback, but also during the optimisation process, there was sort of this knowledge that everything's made of steel, and maybe looking at the alternative composite materials is something that is worth doing. And adding concrete, for example, lighter, cheaper, but then you have the carbon footprint. Again, they are thinking about that, but it is a tricky thing to include in a model. Yeah, future work.
Okay, future work. There's a lot of that. Yes, this guy.
Ajay again, sorry. I've got a sort of reflection, and not sure there is a question about this one to share. Is it Danny? Did you do Danny, can I just say that I really liked your presentation? And the reason was because what I saw in it was you actually thinking about the value proposition. At the end of the day, someone's got to invest in all these things, and you only do those things if there is a profitable value proposition. And I think the key point around tidal and wave is it is a newer technology, it is more expensive. what are the levers to convince people to invest, and what are the levers to get business to essentially support it? I thought the fact that you were accounting for modelling was really valuable, and I'd love to talk to you more about it. I think one aspect is also understanding, for the colleagues in the room as well, as understanding what's happening with the grid and the infrastructure that enables renewable generation to happen as well. So, for example, with your point, if there's a better location to install tidal, clearly it's going to be in the southwest, because you have grid limitations in around the B6 boundary. And then I don't know if you need to attune your device for that space, because there might be different wave and tidal conditions, etc. So I just think the point I'm trying to make is understanding whatever your innovation or your technology is in terms of the overall context of what is happening in the energy system for the UK, and how that picture is evolving over time.
Good, thank you for that reflection. Does anyone want to make a comment quickly?
Well, I can certainly say thank you. But yeah, completely agreed. I think, the transmission network, I'll just pick up on that point. I mean, that's something I didn't present on today, but we're very much looking at that as well, as to how introducing tidal, because it generates at different times to wind and solar, that actually means it could alleviate some of those challenges when it comes to upgrades to the grid, certainly around that B6 constraint. So yeah, certainly that's something we're looking at.
Okay, we've got a question here.
Yeah, I work at Howard University, Southampton. A question for Danny. I'm really puzzled by one of your slides, which is the uncertainty that Nestor indicated around CCS. Puzzled not by your work, but I'm puzzled by the government spending 23 billion for the next 10 years for CCS, yet there is still uncertainty. Can you comment on that?
I can't comment on NESO's publication of that, but I suppose what I would say is I have a similar level of kind of intrigue as to, given the technology readiness level of things like CCS and hydrogen generation as well to some extent, relative to something like tidal stream and even tidal range you could add to that, where we're starting to see the technology readiness level of tidal stream improve, you could argue. There's turbines in the water that have been operating for a while now. So, yeah, weighing up that TRL level versus kind of system value seems really important, and maybe that's an area where it's sort of changing for tidal stream, potentially.
Okay, we have a question there.
Hi, Tom Nightingale from Equinor. To Will first, I think the cable recommendations for burial could lead to quite a lot of additional cost if you're recommending that they're buried further. So would there be future work on the best methods and lowering costs of doing that? I think that would be important for developers, because we see costs increase all the time. And then for Catherine, I think you talked a little bit about concrete and the sustainability side, but then I think my understanding is that could lead to local content benefits and better social value. Is that something that they're interested in talking about as well?
Okay, Will.
Yeah, I mean, absolutely. If you have to install a cable to a greater depth, it's going to cost you more. I would argue our research is not entirely saying that in all cases you have to install to a greater depth. In some cases, I believe that cables are being installed to an excessive depth, and that could be reduced while still balancing an appropriate risk profile over that asset. But we also have to bear in mind the cost. If you do have an interaction with an anchor, and globally there are around 200 cable failures a year, 70% of these are caused by accidental interactions with fishing, gear or anchors. These things do occur. Cost estimates I have for a data communication cable is £10 million plus to repair it. For a power cable, it could be 100 million plus. And you've also got the cost of the lost generation, as well as the safety implications and all these sorts of things. So I think it's about having an appropriate balance of risk, and in some cases it might be worth spending a bit more to get that thing deeper. There's also a lot of complications which I probably shouldn't go into about who owns that asset and who owns that risk, and the person that designs it is different from the people that install it, different from the people that own it, different from the people that underwrite the risk. And so I think more of an awareness and better understanding of the risk and agreement between these organisations is also needed to balance that cost element as well. So it's a bit of a waffly answer, but it's really complicated and it's a really important point.
Catherine, do you want to comment?
Yes, to answer your question about concrete. So we were really excited when we realised as well that the concrete filled double steel tube, which is basically an inner steel tube, and then you have an outer steel tube, and then you pour concrete in. It's actually not very difficult to construct, and it's widely used in industry construction for bridge piers, tower design. They have really good cyclic damping performance, and fire resistance as well. And then the added benefit on top of that was that welding costs also go down. So when you have a cross-sectional area of a circular, hollow section of just steel, you have to weld together all of that area. But then if you then have a concrete filled double steel tube, you have less steel to weld together. And then we ended up, I can't remember the numbers off the top of my head, but I think 5% of the construction cost is in welding, and then you can make like a 1% difference to that. So but there's a whole other changes. So there was a fair bit of interest in having that sort of composite way of constructing these really, really large members.
Very interesting. I have a question here.
Mark Cowley from Blue Ocean Consulting. With respect to burial guidelines, do you think they should be considering the seabed mobility too? Because obviously that changes, and it's an area that's really hard to get developers to take reliable metocean measurements along an export cable route.
Yes. in more seriousness, there are lots of other things that are not considered. So, for example, a cable route is designed, and the depth is designed based on current shipping traffic. You install a wind farm, those shipping routes change, that traffic changes. Over the life of the cable, the size of the vessels change. That's not taken into account. Cellular mobility is not really taken into account, and excess area is a major issue as well for operation of these cables. So my view is it's a difficult area, but it needs to be more nuanced, and more things need to feed into this to get better guidance over the life of the cable. We're talking about something that's in the ground for 25 years or more. So yeah, absolutely, that's something that should be considered. People are monitoring this with fibre optic techniques and looking at changes in burial depths over a cable's lifetime, but it's not really taken into account, as far as I understand, during that burial assessment process at the start of the cable's life.
Good. We'll have one final question. This person here.
Ibrahim from the University Naomi Department. To Catherine, did you consider as a cost saving in cost reduction in operation and maintenance in your study, or only the cost reduction in the design?
Only the cost reduction in the material requirement and also the welding requirement for a particular support structure.
Okay. Do you expect more cost reduction for your future work, especially for more configuration for the TLP in operations and maintenance?
Ooh, haven't done modelling, so I wouldn't say hard yes or no, but probably. Future work, I'd say.
Okay, I don't think there are any other questions. If there are, please speak to our speakers over lunch and really grill them about what they've been doing. I think it's been very interesting and enjoyable to hear the research, so can we just give them